with contribution from France and Canada. Alain used extensively, I think we can say that, the Hubble Space Telescope, and thanks to these programs, Alain is very well known in the community for his work that really pioneered all the first observations of exoplanets' atmospheres. This is one thing, and the discovery of the evaporation, of their evaporations. Yeah, there is another field in which that benefits from Alain's work. This is the field, the search for exocomets, and this is the topic of today's seminar. So je te rends la parole, Alain.
Thank you very much. Thank you very much. Do you hear me? No? It works now? Yes. It's okay? So thanks very much, Clément, for its introduction. So I must yes. Return the politeness. And I must introduce Clément, so you can come here, Clément, to you. Clément has just been hired at IEP as a maître de conférence at Sorbonne University. So we are very happy to have him now here in the team of Exoplanet, working on exoplanets. And he's working on the discovery of exoplanets using microlensing. And looking for a picture of him on the internet, I found this picture. And you see that he's well involved in teaching to young people here in a classroom of 15 years old people. And he was collaborator of NASA this time, working at Goddard Space Flight Center. And the last sentence I noticed is in French. Être chercheur, c'est comme faire un exercice de maths dont on sait qu'il n'existe aucun corrigé. I'm not sure I fully agree with this statement, but we may discuss later about it later. Thank you, Clément. So now we skip to exocomets, and I entitled this presentation 35 years of discoveries. As you will see, there are really many discoveries for 35 years, and many of them have been done here at IEP. And they've been done here at IEP because of very clever people, including Alfred Vidal-Major. And this Alfred Vidal-Major, many of you know him. This week is the week of his 80th birthday. So Alfred Vidal-Major, I know, looking for us from distance now. Good, happy birthday, Alfred. And Alfred has done many achievements at IEP, discovery of the local interstellar cloud in which the sun is embedded, discovery of exocomets I will show you, and also the discovery of atmosphere of exoplanet. And today, this is also the 20th anniversary of the discovery paper of the exoplanet evaporation, which has been published by Vidal-Major and his collaborators at IEP. So, and after presenting the key people working on this subject, I want to show you the last slide of the presentation to show you the most recent result we obtained on this exocomet. And just to give you a flavor of what you will learn by looking attending this conference, this colloquium. And so after you can, if you wish, you can sleep, and we go to in 45 minutes. I will detail this result. In short, earlier this year, we published the exocomet size distribution in the Beta Pictoris planetary system. We measure the size of the nucleus, few kilometers size, rocky bodies evaporating around Beta Pictoris, and we measure the size distribution with a power law of 3.6 plus or minus 0.8. But what is really amazing is that this result is exactly similar to what we measure in the solar system, which is shown with dotted lines here. And the blue point are the measurements with 30 exocomets for which measure the size of the nucleus. And this is the typical law we expect for bodies produced by fragmentation. So this result shows that the size in the asteroids, comets in the solar system, and the size of comets in Beta Pictoris are the proof that collision play a major role in shaping these bodies at the late stage of a planetary formation. So why looking at exocomets? You know, comets or asteroids, they are small bodies. So you may say, oh, this is only a fraction of the mass in planetary system. So why do we care to look at them? So in fact, these bodies are two major roles. First, there's the building blocks of planets. So there's the remaining parts of the block, the planetesimal, who produce the massive planets we observe in the extrasolar system. And also, in the other way around, they are the result of fragmentation, as I showed you in the previous slide. So this is, they play a major role in building blocks, building planets, and fragmentation. So understanding comets and asteroids in planetary system is a key of understanding the history of this planetary system. And also they play a very important role in transportation of material. And you know that on the Earth itself, we have water because this water has been brought by fall of minor bodies, asteroids or comets, which were rich in water. So the water on Earth, there are very, very little water on Earth, but it has been produced mostly brought by comets and asteroids. So, and also these asteroids and comets play a role in interaction with smallest bodies, dust, gas, and interaction with larger bodies, planets. And so it's a link between all the constituents of the planetary system. And we should not look at planetary system as a star and planet, but as a full complex system in which small bodies like asteroids and comets play a key role. So why we are able to detect those kilometer-sized bodies around other stars? You may think, oh, is it possible to detect those? Yes, it's possible because they are comets. And in comets, in the solar system, it means, from historical point of view, a comet is a small body evaporating, and what you see on the sky is a tail, is a big, huge tail. So comets are small bodies evaporating, producing tail of gas and dust. We'll see in a few minutes. So they can be detected when small bodies can be detected when it becomes a comet, an evaporating body. And because the tail, the evaporating tail on coma, makes a size of a million kilometers, and we have the transit of those million-sized gas and dust. We can detect it when they transit in front of the star. And as you know, comets are two major constituents, and this is the key in this presentation today. There is the gas, which we can detect through spectroscopy, and there is the dust, which we can detect through photometry. So transit of comets observed in spectroscopy will allow us to detect the gas. Transit of comets in photometry will allow us to detect the dust. And there is a key, not a key person, but a key star, a star among the stars in all this story, which is Beta Pictoris. many of you have heard about it, but I want to present it to you shortly. This star is really amazing. He has three main properties. It's a close-by star, 20 parsecs. So magnitude slightly less than 4, seen by night eye. So you see there are thousands of stars you can see by night eye. So it's not uncommon, of course. Each age is about 20 million years. It's a young star, and there are, of course, in the galaxy, many, many young stars, as you know. He has a planetary system which is seen exactly edge on. Every object orbiting on the star in the plane of the system will transit seen from the Earth, which is not uncommon. We detect thousands of planets transiting their star. So having a planetary system seen edge on is not uncommon. So all these three properties are very common for thousands, millions of stars in the galaxy. But having three of them collected in the same star is a miracle. We living on the Earth, we win the lottery of having such an amazing system. So we look at it for 38 years now, and we have made many discoveries thanks to this amazing planetary system orbiting the star Beta Pictoris. And all this story, I will tell you today, started in October 17, 1984. The disk around Beta Pictoris has been discovered by Brad Smith and Richard Terrell, and they published a paper in Science, and it makes the news of the International Herald Tribune in October 17, 1984. Another miracle. That's why I'm here today. Roger Ferlet here in the room, and Alfred Vidal-Majar was on the plane going to Chile to observe the interstellar medium. And they observed the interstellar medium by absorption spectroscopy. They are experts. They discovered the local cloud of the galaxy, as I told you, that way. So these two guys enter the plane and they take the journal. What they see is amazing discovery. They said, wow, if the disk is seen edge on, we'll point the telescope, we'll make spectroscopy of the disk. A miracle, you know? And they make it, and they discovered exocomets. So, as I told you, there are the way we can detect exocomets through spectroscopy to detect the gas. That would be the first part of my talk. And we can detect also the dust using photometry. That would be the second part of my talk. So let's start with the spectroscopy, which is historically the way we detected exocomets 35 years ago. That's the picture of the first spectra published for the discovery of exocomets. I can spend a little bit of time on this because it's the key to understand what we do. Here you see, this is the spectrum of Beta Pictoris obtained with the spectrograph in 1984, October 20, you see, just 3 days after the Herald Tribune paper. Because at that time, you know, you were to the observatory, you plan to observe stars for interstellar, close by interstellar medium, but you can use a little bit of your time for another interesting target. And that's what they did. And they make the discovery. And you see, this is the spectra of October 1984, October 20. And this spectra, the thick line is here. It's composed of the spectrum of the star, the broad line here, in calcium-2. This is the line of calcium-2. So it's broad line, which is broadened by the rotation of the star, the spin of the star. And right away, in October 20, 1984, they discovered that there is a thin line here. This is the gaseous component of the circumstellar disk. So right away, they made the discovery of the gas orbiting Beta Pictoris in the disk. But what was amazing, and it takes them few years to understand what is happening, is that when they make spectra at different dates, you see November 1984, 85, 86. There are variations here, and there are additional absorption at large radial velocities, which appear and disappear within our time scale. So you observe it, 2 hours you observe, it disappeared. So what is happening? Some gas is in front of the star appears, disappeared at high radial velocity. So this is the explanation. The first time that the word comet has been written in a paper was the paper by Roger Ferlet and collaborators in 1987, so 35 years ago. Roger and collaborators wrote, this could be due to comets, which at that time was, you see, 8 years before the Bayer and Kellos discovery of 51 peg. It looked really crazy. How can we claim to detect comets on another star? So it takes time, but they convince people that that's really comet thanks to simulation. This is another part of the story. We'll see in the second part for photometry that here at high P, we are lucky to have combination of observation and simulation to support the interpretation of this observation. And the combination of two makes the discovery. And that's what happened for this exocomet. Hervé Beuys and Marie Lagrange and so on produce simulation of transit of exocomet, and they explain the variable absorption lines through this simulation of evaporating comets. And you see, this is the result of simulation, which really look like what we observe in reality. So the combination of two make a convincing case that we really detect exocomet transiting Beta Pictoris. And there, after many, many observations, so I will not describe, I would need 4 or 5 hours to describe all the results which has been obtained. One result which is interesting, just to show you how we work and to show you how we are really convinced those are exocomets. The Hubble, as mentioned by Clément, we use Hubble many times. And in 1984, we detect many, many lines. So all these lines are very interesting. But I will focus on one line, which is the magnesium-2 doublet, which is been observed at 2 different dates with Hubble Space Telescope. And this is a doublet. So there is an absorption line here, an absorption line here. And there are 2 observations. So this magnesium-2 line, K and H line. Observation 1 in blue, no transit comet. So the full spectrum of the star. Observation 2, another date, a comet is transiting. So there is an additional absorption in the 2 lines here. And you can make the ratio of the 2. Here is a plot of the ratio of the 2 for the 2 lines. Magnesium K line here. Ratio of the, so this is the spectrum of the comet you observe here. And making the ratio without and out comet, you have the observation, the ratio of the 2. And what is amazing here is that they are exactly similar, while the oscillator strength of the 2 lines is a ratio of 2. So you expect to have one which is much deeper than the other one, except if they are saturated, of course. But if they are saturated, they go to 0. The absorption is saturated to 0. No, it's not the case. So the only explanation is to have a cloud which is optically thick, but doesn't cover the full surface of the star. So it shows that we have a cloud of gas which is optically thick and smaller than the star. This is fully interpreted by theoretical modeling as made by Hervé Beuys and collaborators. Here is the prediction. And you see, basically, here you have a cloud which is covering about 60% of the star, optically thick. And that's all. One of the many, many examples I could give to convince you that really we observe directly transiting of exocomet, the gaseous part of the transiting of exocomet. There are many, many other observations. I will go fast, but I will not detail. Oops, sorry. So the velocity, we interpret many different properties of this gas, the radial velocity, the time scale, the size of the cloud, as shown you a few minutes ago, the temperature of the gas, the presence of over-ionized species, all has been the matter of many, many papers and many work to interpret all of this and to have a very close-by look on this exocomet. The last one I want to show you, which is in my mind quite interesting, is the presence of CO. We detect on Beta Pictoris the gas CO. Observed first, now with Alain we detected, but first it was observed with Hubble in UV because there are electronic lines, electronic transitions. So we can observe many bands of CO. That one of the paper by Joly and collaborators in 1998. You see all these absorption lines of CO, this CO in the gas disk of Beta Pictoris. And I can tell you that even last week with Alfred, we still work on this CO observed with Hubble. We have many, many things, very interesting things to work with, to work on for the coming months or weeks and months. But let's say for this CO, first detected through the UV lines. We have a measurement of the temperature. We have also a measurement of the 12 CO to 13 CO, which is with a V-slow ratio, is a proof that this gas is produced by evaporation of bodies at low temperatures where there is fractionation between the 12 CO and 13 CO. And I told you, just mentioned the last sentence, this CO is produced by evaporation. We have a proof that this CO is produced by evaporation of solid bodies, which has been made thanks to the FUSE observation. The FUSE is a UV satellite launched in 1999, sorry. And we observed Beta Pictoris to search for H2, the gas H2 in far UV, and we didn't detect it. So we make an upper limit on the H2 content. And what is interesting is that the ratio CO to H2 is much, much, much larger than interstellar medium. And this shows that the CO is not protected from the UV field, which destroys the CO molecule. In the interstellar medium, you have CO only when you have enough amount of H2, which protect from the UV lines, UV field, radiation field, and which avoid the destruction of the CO into O plus C. So here it's not the case. So the lifetime is very short, less than 200 years. And so you need, the CO we observe has been produced less than 200 years from now. So you need the production of already formed molecules. And the best way to explain it is, of course, the evaporation of frozen molecules in comets, which evaporate when they go close by to Beta Pictoris. And we have made many, many other work on this. I want on individual comets. But at the end, we have many, many detections. And Flavien Kiefer, here in the room, had the idea to look at all these detections to make statistical studies. And he made these studies of more than 1,000 spectra and collecting with the ARP spectrograph. And looking at those, he detected a total of almost 500 exocomets. I don't know the number, it's 490 something, almost 500 exocomets. And looking at those, we were able to show there are two different families of dynamical families of comets. You see the lines, this is the plot I got from the Flavien's paper. So this is in red, this is the spectrum of the star in the two lines, and red without any comet. And you have comets detected simultaneously in the two lines. This is the key point. We are able to detect the key point. And as for the magnesium, this allows to measure the size of the comets, of the clouds of the comet, not the size of the nucleus, but the Gaussian cloud of the comet. And you see the deep lines called the D family, and there are shallow lines called the S family. Deep is in blue, shallow is in red. And if you measure the evaporation rate, evaporation efficiency, how the nucleus transforms the capture of the energy from the sun, from the star to evaporate H2O. And there are two different evaporation efficiency for these two family of lines. There is even more interesting, I think. We can plot, we have, because we know the velocity, we have an indication of the orbital properties of the comet. So we know the periastron distance and the longitude of periastron. So we can see the orbits, this plot, the two parameters of the orbit. And you see all the blue ones, which are evaporating very efficiently, are the same, have the same orbit, basically. While the red one, the shallow line, are very low evaporation efficiency, and they are tail of distribution like that. And here we plotted the prediction of bodies on the 4:1 mean motion resonance predicted by Hervé Bos before we met that. No, and we see it's amazingly well following this picture. So we have now the proposed explanation for these two families. One could be the result of fragmentation of big bodies, all bodies on the same orbit and with a high evaporation efficiency because they are new material exposed to the starlight, while the second family is a family of bodies slowly going closer to the star on mean motion resonance with a planet which could be Beta Pictoris b, discovered by Anne-Marie Lagrange and collaborators about 10 years ago. And Flavien did not only make discoveries of these two families, he also discovered the second case where we are, because I speak about Beta Pictoris, you have many other stars. And Flavien used archival data against of ARP to discover the transiting comets in front of the star HD 172555. This is the discovery plots of the absorption lines. This is the ratio of the without and out and with comet and without comet. So this is the absorption comets. And we have the two lines, which is the key to really constrain the gas property and to be sure it's comet, transiting comet. And later on, team from the US, led by Carol Grady, make Hubble observation, and they also observe, you see in the carbon 2 line, this absorption, confirming this is really transiting comet in front of this star HD 172555. There are many other stars. I'll show you this, I will go shortly. This is done by people in the US with Aki Roberge for the star 49 Cetus, sorry, 49 Ceti. And you see absorption in the carbon 2 lines here, and they are well explained. We have also calcium 2 lines taken from the ground-based telescope. So we are pretty sure that those are exocomets transiting the star 49 Ceti. So, second part of my talk, I told you, spectroscopy allows to detect gas, photometry allows to detect the dust. And that's the big news for now. News? Not exactly, because we work on it more than 20 years ago. It happened in 1998, 1999. At that time, it was planned to launch spacecraft to make very precise photometry of stars to look for transiting planets. The first of these was Corot satellite, launched by the French space agency, CNES and ESA. And so at that time, the launch of Corot was in the plan. And I thought, oh, that's interesting. We detect transit of comets in spectroscopy. What can we do with photometry? So I wonder what would be the photometric light curve of a transiting comet. In this case, in photometry, this is the dust. We make a decrease of the starlight. And I make these two papers. And I, just to underline, because 20 years later, it's difficult to realize, but I underline at that time when I published those, there was even no transit of exoplanet ever detected. No, it was before the first detection of an exoplanet transit, which has been made in September 1999. So it was months before the first detection of a transit of an exoplanet. Okay? And but I questioned myself, what is a transit liker? And I produced, this is for the first paper, you know, this kind of liker, which is easy to understand. When you have a comet, you have first the head of the comet transiting the star, which is optically thick, small, but optically thick. So the decrease of light is very sharp at the beginning. And after, when the head of the comet has finished its transit, this is the tail of the dust, which is transiting, which is low, with low opacity, low. So the return to the normal brightness of the star is slow with this kind of curve. So, okay, it's quite easy to understand the main shape of this light curve. So that's all. And to say this paper, I was very proud of it. And in the evaluation of CNRS and so on, I often cited it as a paper. I thought it was something, I was proud of it, simply. But it was cited once, maybe twice by other people. No one cares. Okay? No one was interesting, but thought, oh, that's interesting to have this prediction. Or I give you the details of the calculation. So for this calculation, that's the need of simulation, you know, like for Weber's work for exocomets in spectroscopy. So we need some physics, size distribution of grain, radiation pressure, the excitation, there is some physics. And for this complex physics, with complex optics, you need simulation to do it properly. I just mentioned here at the end of this slide, the size distribution of exocomet. And you see, even time I had the idea that we have to take care about the size distribution of the core of the comets, here RC, the nucleus of the comet. And I put a power law with a gamma 3.5. Okay, in this paper. And so that's the light curve I just described. And okay, but at that time we didn't have a spacecraft to make measurements. And the Coro sensitivity accuracy was not good enough to make those detections. But fortunately, Kepler mission came out, and Kepler was successful. And we have measurement at 10 to minus 4 accuracy, which we need. Oh, I show you the, we see it's 10 variation of flood. The amplitude of 10 to minus 4 is a few 10 to minus 4. So you need something extremely accurate to detect those. And Kepler came out, and this is this Boyajian star, kick number, I never remember. And they detected a very strange deep variation, totally random variation. They were not able really to explain. And even when they make the press release, they say, we have no physical interpretation. That might be artificial intelligence, you know. And we heard at the radio, maybe they detected artificial intelligence and so on, which is, I will say not here what I think about this kind of interpretation, to be polite. But there are good interpretation by other people saying, oh, this could be comets transiting. And with that in mind, with Flavien Kiefer again, the guy came out and said, oh, we look at this data carefully. And what we noticed is that in this, for this star, there's been two kind of dip, small dip, about 3 years apart, which look very, very, very similar. So this is possibly the first detection of a periodic transit of an exocomet. Unfortunately, since then, we have not been able to observe it again because the observation window of Hubble Space Telescope never it was always off because every 3 years. So, and each time it happened, Hubble Space Telescope was not possible to be pointed toward this star. That's unfortunate. But we interpret, thanks to the simulation we have made, we interpreted those with a transit of a string of exocomets, not only one. We need a string like Schumacher-Levy, which is common when you have fragmentation of bodies. We have a string of comets. So, and Flavien showed that this light curve can be well explained by 5 to 7 comets with a evaporation rate which is similar to Hale-Bopp. So we have a string of Hale-Bopp comets transiting in front of the star every 3 years. And other people have looked at this Kepler data. One guy was crazy enough to look by eye at all these light curves to see if there is something strange. And he detected 2 stars with funny random transits, which look like, you know, this light curve, you see? So there are 6 possible transits of comets in front of this star detected by Rappaport and colleagues at MIT. And so for these 2 stars, there are 3 big transits. The first one here, and 3 shorter and shallower transits, corresponding to a total mass about 1 Alain mass, evaporating in about 300 days on an exocomet in front of another star, which has been detected by looking at this data with your eye. That's an amazing result, I think. And so we have simulation in hand. So with Lucy Crow making an internship here, we look at this data detection made by Rappaport. And one of these, we made for all the 6, of course. And one of these, for instance, could be interpreted by the transit of 2 comets right away following one to the other. And we have typical production rate of dust, a few 10 to the 6. And we have orbital parameters to interpret this light curve. So this is a work still in progress and should be published probably next year. And after Kepler came the other photometric satellite, the amazing TESS satellite. And TESS changed the game tremendously. With TESS observed Beta Pictoris for 120 days about. We are lucky because it's a good part of the sky to be looked with TESS for a long period of time. And Ziba and collaborators published this paper in 2019. And I show you here the transit, the most beautiful transit of exocomet observed in photometry up to now, which is here. This is a plot taken from their paper. You see the light curve, and recall here the light curve we produced 20 years earlier. It's exactly what we so just looking at those, making the comparison, make a convincing case that there is no doubt this is transit of exocomet in front of Beta Pictoris, where we observe not the gas, but the dust. And the dust is very interesting because we can make different measurements from it. We can make the estimate of the nucleus size. So after this publication, which has been made with TESS observation in 2018, so we say, wow, wonderful. What's a great idea to look at Beta Pictoris TESS data. Other people did it, very nice. But TESS observed a second run in some way, a second sector at the beginning of 2021. Say, oh, we will look at those data. So that the observation made by TESS in 2018, here you see the transit I've just shown you. which is obvious to detect. And there are many other data taken in 2021. So with Lucie Crowe and Guillaume Ebrard, we look at those data and we search for comets. And I must say that for that, we were well prepared thanks to the simulation. We know exactly what we were looking for. And that helps to make those detections. And at the end, we detected transit of 30 exocomets in the total of 1,056 days of observations. And after some calculation, from simulation, we can transform the absorption depth into evaporation rate if we know the periastron, the mass of the star, of course. So there is a direct relationship between the light curve and the dust evaporation rate. We can make a calibration using the Hale-Bopp, for which we know exactly the size and the evaporation rate, which is the best case for a precise measurement in the solar system. Even in the solar system, knowing the radius of the nucleus is difficult, you know. But for this, we have 30 kilometers radius for Hale-Bopp. And so we can convert this light curve into an estimate of the nucleus, of the size of the nucleus. And this is the distribution of the absorption depth. You see, we have much more low absorption depth, decrease of light during the transit, very large number of low absorption depth and less number of large absorption depth. And we can convert into diameter. And we see, so we have one comet with a diameter between 8 and 10, one between 12 and 14, 4 between 6 and 8, 8 between 4 and 6, and 16 between 3 and 4. In fact, we have a distribution of the radius. And that's what I showed you. That's really the major result I wanted to show you today. So which published earlier this year. So this is the distribution. This is the power law to be compared with observation in the solar system. And you know, this number, the power law, is so important that many people in the solar system are putting a lot of energy to measure it in the solar system. You see, all these papers have been published in the like 10 years. Even in the solar system, it's a key point to measure the size distribution of asteroids and comets on different families of comets and so on. There are much more detailed, of course. But this is really a key measurement. This is the same. That's the fact that it is the same is important not only for Beta Pictoris planetary system. It's also important for the solar system, because having the same value shows that this value in the solar system is not by chance. It is a proof of something. And this value, 3.5, is what has been predicted by Doinayi in 1965, for bodies produced by fragmentations. So this is a proof that all these bodies are produced by fragmentations. And of course, so this is the end. Now I'll show you a few slides fastly, quickly. What we are doing now, what will be the story for the coming weeks, months, maybe years. We didn't observe transit of exocomet only in front of Beta Pictoris. We have also the Cheops satellite, in which we are involved. This is the ESA mission. And with Cheops, we are able to make measurements of photometric measurement of HD 172555. And Flavien again is working on it, and he detected something which really looked like a comet. So it's something, a hint of a detection of a comet with a radius of the nuclei about 2.5 kilometers. And a production rate of few tens to the 5th kilogram per second. And we have made new simulation. Of course, this simulation, you have to realize, had been made 20 years ago. So with the computer were slightly different from the computer we have now. So I made new I produce new library of light curve and using those with the help of Pierre Dumont. We use it to make a search for comets in Kepler data using neural network. And after some very accurate work made by Pierre Dumont, we are successful. And it's not announced yet, but we have a good list of stars for which we have, I'll show you this example. And so we are still working on it, but keep in tune. We probably announce some detections using this Kepler data and a new way to look at the data. And of course, we still keep working also on the gas, and we will observe with the Hubble Space Telescope the star HD 172555, and this is scheduled to be observed by HST in March and July, between March and July 2023. We'll have 8 visits in this time frame. We hope it will be scheduled. Maybe it will be later sometimes with Hubble. The schedule get reported, but okay. And skip that. And so what is the next challenge for these exocomets? What is the key question we want to solve? There's a question about the properties of these bodies, the measurement of dust to gas ratio. This is one of the key points we want to try with Hubble Space Telescope for Beta Pic and for HD 172555. We want to measure the abundances. We have many, many lines of carbon and oxygen. And really, we are still working on it. And I'm very hopeful that we'll get some interesting measurements there. Of course, the size is still a key property, the physical property of the nucleus and so on. And this is for the bodies, but we are also key questions regarding the relation between those bodies and the planetary system in which they are. Most of these are detected in debris disk. So of course, there is a relation we need to better understand. And of course, the interaction with planet when they are detected, like Beta Pictoris B and Beta Pictoris C. And for doing all this work, we have many instruments to do so. So I skip very fast. Of course, Spirou spectrograph, BLT, the TESS, which has been launched in 2018 and working well. The Cheops satellite, launched on December 2019 and working well. And we are planning the extension of the mission starting from September 2023. So really, this mission is working well. I just came back from a science team meeting of Cheops, and I can tell you that this mission is really amazing. We plan to do many new observations of debris disk stars and exocomet stars. And of course, you all know that James Webb is very successful. So we hope to be able to make measurement of exocomet with that. And for the ground, ELT will change the game for sure. And at the end, last slide, the space mission. And we are lucky to have 2 ESA space missions in which we're involved. We are involved both in Plateau and, of course, in Ariel. And the combination of 2, I've shown you. Combination of 2 is wonderful. Plateau for photometry and Ariel for spectroscopy. So we are very in good place to do the key science in exocomet in the coming years and decades. And that's all.
Thank you, Alain. This was very interesting and exciting. Just the first question, is somebody checking questions online at the same time? Okay, so have you some questions? Maybe we can alternate. I will start with
Thank you very much. It was a very interesting talk. I didn't understand. So you talked about detection in spectroscopy and then in photometry, but what about the combination of the two? For example, I was thinking in the case of the string of exocomets, you know, there was that feature and you observed it in photometry. I mean, the natural thing would be to look at that in spectroscopy.
It would be great to have both simultaneous photometry and spectroscopy. We tried sometime, but we never succeeded to have a simultaneous detection of these two. But anyway, just to mention, to have time on typically space telescope combined with photometry survey, because you know, for photometry, you have the space on TESS, you don't point. There is a fraction of time, so it's not, and you have to have simultaneous, and you have to have time on the good telescope. That's not easy, as you know. The pressure on Hubble Space Telescope, I don't speak about James Webb, but it's extremely high, so it's difficult. We tried, we never succeed to get it properly, but still, I can mention one nice result here is that for this comet, you know, detected in photometry, we make the comparison of the properties with the comet detected in spectroscopy, measured by Flavien, and we are sure that they are exactly the same kind of, they're similar, you know, in evaporation rate and so on. So it makes a good sense that this comet would have been detected if we had the chance to have spectroscopy at that time. So we try to do it. We never succeed up to now. There is hope also for this program, because this star will be observed in June 2023 by TESS. There will be a full month of observation of this star in June to July 2023. So we'll have Hubble Space Telescope observation, TESS observation. I scheduled one of the visits to be in the same time frame. I hope it will be scheduled at that time frame, but who knows, you know? Even TESS data, TESS observation is not fully continuous. There are some breaks and so on. So let's hope it's possible for the future, close by future.
Thank you. That's probably a very naive question, so I apologize. But when you showed the Beta Pictoris star with the disk around, the first thing that came to mind for me was the Parker instability in a magnetized disk, which can produce outflows. And you also mentioned the Parker instability. When you have a magnetized disk, there's an instability that drives outflows, and to what extent you can see such a signature?
You know, these disks are extremely thin, they're optically thin, so there is even very little collision between dust and interaction with the gas and so on. So basically, the physics of this dust particle in the disk is simply Kepler orbits. Okay. So
not a plasma of gas.
No, there is no interaction between the dust and the gas. So it's in fact the physics of all this is extremely simple. It's first year of university level in mathematics and physics. I'm sorry, I don't do difficult physics. I'm just using the Newton physics, I would say. Yes.
Alain, thank you very much for composing this very nice story, because it's not hidden to anyone that you are the guy behind all those discoveries, even though I published some of them, but you are the one at the wheel going towards these discoveries. So thank you very much for this. And I wanted to add a few things about simultaneous spectroscopy and photometry. We have to mention the PIXSAT mission that was not a success, unfortunately, because it failed, but actually I don't know how it is now because apparently it survived somehow. But we had a program to make simultaneous spectroscopy and photometry using ARPS spectrograph and PIXAT that was supposed to follow up the photometry. So,
but the hope to have a resurrection of PIXAT is extremely low, I think.
It died.
Yeah, in fact, they don't know what happened to it. There may be some cosmic rays at the bad moment or whatever, so they don't know. What is very small hope is that somebody capture a signal from it, so it's still to be alive, but I don't know how they will be able to revive it. So I don't know. And there's been a proposal for a second, for launch of a second, and they said that having TESS, is it worth to produce a CubeSat to do something quite similar while you can use the TESS data? Of course, the range of time frame of TESS is not as big as what we could do if we produce a dedicated mission. So having it would be certainly very nice, but anyway, that's the life of space mission. When a space mission is in trouble, it's difficult to go there and to repair it.
And so I had another remark, last remark, on KIC 8462852. Actually, it's even worse than what you said, because we tried to observe the transit with Hubble, but we also tried at first to observe it with Spitzer.
Yes.
And actually Spitzer was stopping its operation just before the transit was supposed to happen.
No, but one transit every 3 years makes the things very difficult to schedule, for sure. Maybe questions on the line? No, I don't know.
Yeah.
In your radial distribution, it seemed like there were some features. Are these like there were some bumps in the radius distribution of the comets? No, yeah, the nature paper here.
Here.
Yeah, there seems to be like.
Oh,
yeah. Is this within error bars?
Each data is one comet, so I would not claim something significant here. One thing is here is almost significant decrease here, but I don't know if it's due to the detection limit. Here are the smallest bodies, so probably the efficiency of detecting smallest bodies is slightly biased. So, you know, having the power law is the result. Going beyond that, I would be extremely doubtful. You know, we should not interpret this kind of more than the power law, which is in itself enough important result.
There is a question online. No more. Any other questions?
From all the comet transits that you observed, do you have a way to decide if you have seen the same comet transiting several times, or if this is impossible?
No, except for the one we detected in photometry. For the other one, it's really impossible to know there is some period or whatever.
Other questions?
There have been some work by Hervé Beust to try to understand if there are some periodicity of the comet rate, the number of comets per unit of time, and if there is some modulation, because there are some prediction of this modulation in the case of resonance with a planet. So there has been some try to find it, but as far as I know, I never see a convincing result on this.
Well, thank you again, Alain, for this very wonderful overview on exocomets. I think I never heard of so many details on exocomets, so thank you. Let's applaud again. So this was the first colloquium of the semester. Next week, there's Clifford Will coming and giving a general talk on the renaissance of general relativity, so that you all will come. So thank you again and have a good weekend. Bye. Oui, je vais.
Ouais, alors en plus, il y a probablement très peu de champs magnétiques, c'est une étoile A. Et